Chapter 4. Logic gates and logic circuits. It is logic. Let's see. Do you know mathematics? Yes. Okay. And do you know logic? Logic? What is logic? Let's have a look at this. Is this door? You can see this picture on my screen here. And is this door fully open? No? All right. Another question. Is this door fully closed? No. Then what is it? Is it half open? Yes. Huh? Correct? You agree, no? It's half open. And is it half closed? Yeah, that too is correct, no? Half open, you can see. And you can see that it's half closed, not fully closed or not fully open. So we can do something here. We can put it as an equation because half opened is half closed. It's the same, no? Half opened equals half closed. What happens when you multiply both sides of the equation by 2? According to your mathematical knowledge, 2 multiplied by 2, both sides gets cancelled. No? These two, the half, these two and these two gets cancelled and cut off this and that. And then it becomes 1. That means whole. 1 opened equals 1 closed. Or in other words, open equals closed. Huh? Is open equals closed. See, but this kind of logic, but let's see, what we are going to learn is little different. It's more scientific than what we just saw. What are we going to learn? Learning objectives. At the end of this chapter, you should be able to use logic gate symbols. So there are new things to learn. Logic gates and logic gate symbols for these logic gates. What are they? Not logic gate, and logic gate, or logic gate, NAND logic gate, NOR logic gate, and XOR logic gate. Or this is another word for XOR is exclusive OR gate. Now itself, I'm telling you, NAND is not AND. If this is AND, this is not AND. Like good and not good. For good, the opposite is bad. But we can also say not good. Good, opposite is not good. Same way here, and another gate, the opposite of it, not and. Same way here, or and not or. So they are called NAND and NOR. Understand and define the functions of the not and or, NAND, NOR, and XOR or exclusive OR gates. Then you will learn to construct the truth table for each of the above logic gates. There's a thing called truth table. You will learn that soon. To construct a logic circuit from these things. Logic circuit. So the computer works on all those things. Are logic circuits, electronic circuits. They are logic, producing logic and arithmetic and all that. So construct a logic circuit from a problem statement. So that also you have to learn what a problem statement is, what a logic expression is, what a truth table is. From these three, or one of them, you can construct a logic circuit you can draw. Then also construct a truth table from, that is this truth table here, from the others. A problem statement, a logic circuit, or a logic expression. So these are like jumbled here. And construct a logic expression from a problem statement, logic circuit, truth table. So all these are the same in different contexts, right? Jumbled off, one from the other. Boolean logic and problem statements. So as mentioned, we learn what logic problem statements, Boolean logic, and all that. First of all, there's a thing called logic proposition, a statement that is either true or false. Colombo is further north than Singapore. It's true. Yeah. Any statement can be either true or false. This is a statement that is either true or false. But in this case, Colombo is further north than Singapore. It is true. If you look up the world map, take the equator, and a little below, you can see Colombo as well as Singapore, and which is further north. Like that, you can below or above. I don't know. I can't remember. My geography is not so good. Right? Maybe above or below the equator, but definitely it's further up north than Singapore. Singapore is south, Colombo is north. Then you have a thing called problem statement, an informal definition of an outcome which is dependent on one logic proposition or a combination of two or more logic propositions. So now look carefully and remember. So logic proposition is like a statement, right? Proposition, like a statement. This Tom is older than his mother. Somebody makes a statement. Tom is older than his mother. But can it be true? You have to think. You have to think. You have to get the meaning when you read or when you listen to me or when you even read a book or some lesson. Every word you have to picture and you have to concentrate first of all, then see whether this is correct. Can't be, no? Tom can't be older than his own mother. It's false. Then the problem statement comes. An informal definition of an outcome which is dependent on one logic proposition or a combination of two or more logic propositions. So one or two or more of these things that is made up, the problem statement is made up like that. So here's an example. You should take an umbrella if it is raining or if the weather forecast is for rain later. So if it is raining, must take an umbrella. Or the forecast says it will rain in the evening or later. Then you must take an umbrella. So another one is buy fish which is fresh. That means if it is fresh, same thing. No? Fish which is fresh, and if the price is less than 25 pounds per kilogram. So now make use of your knowledge about flow charts. Let's see how you can relate it to this. Then it's easy to remember. I'm reminding knowledge, two things. Knowledge is made up of two things. The learning. First of all, maybe that you have forgotten or I may not have told you before. Studying and learning are two different things. Studying is useless just for the exam. You study and do the exam and you forget what you learned. 2 weeks after the exam, if you are given the same paper, you can't do it. What's the use? Without knowledge, you are doing the exam and you study. But if you learn, that becomes knowledge, which is permanent. Whether you do the exam or not, you are knowledgeable. So how can you make it knowledge? How can you learn, in other words? Learning also has two stages. First is understand whatever that you learn or hear, listen or read. What you hear or read, you must understand. But that is easy. That part is easy because you are intelligent. You will easily understand what the teacher is saying. Second part is, can you guess? Remember that part. First part is understanding. Second part is to remember that. You understand something very well. The next day, if I ask you to explain it or ask a question on that, if you can't answer, what's the point? You're understanding? No point. So remember these two things. Understand, but you have to remember. So For that, you must know the meaning of each word that you hear or read. So if you relate this, another way is to relate something that you already know, and then it's easy to remember. So flow chart. Fish is fresh. Is fish fresh? Yes. All right. Okay. Then we continue. Otherwise, you finish somewhere at the end or whatever. I didn't complete this diagram. But no, that's the end of it. But here, if it is yes, then there's another question. It's a price less than 25. If it is no, still finish. That's gone. Just because one is okay, no problem, no use. But this is also correct. If it is yes, then buy fish. And then do whatever, right? Go home or whatever it is, right? That's the end of it. Now the Boolean operators. Boolean. Boolean. You know what Boolean? The mathematics and all that. You have done Boolean algebra. Logic expression. So here's another one. Logic expression. Logic propositions combined using Boolean operators, which may be equated to a defined outcome. So here's the textbook. Please taken from the textbook. Word example. 0.01. Construct logic expression from problem statement. Logic expression from problem statement. We know what a problem statement is. A shopkeeper, this is the problem statement. What is written here? But we have to construct a logic expression from that. So the statement is, the shopkeeper orders a delivery of goods at the end of each month. Shopkeeper must buy, you know. He can't just go on selling without buying, right? Unless he produces. But generally, shopkeepers don't produce. Manufacturers only produce. They are called manufacturers. And shopkeeper is just a point to sell out. Huh? So shopkeeper orders a delivery, that is, from the supplier, say, okay, send these goods at the end of each month. Okay, that's one statement. Every end of each month, he orders. Here's another case. If the stock of a particular item falls to the reorder level before the end of the month, a delivery is ordered immediately. What does that mean? Because you can't wait till the end of the month. If one item goes out of stock, you can't send the customer back. Can't send him empty-handed. He will go to the next shop, and then if he finds that it is cheaper or better service or better quality or something like that, that customer will not return to this shop. So it's a risk of losing not only that sale, but the customer too. Customer also will be lost. He will not come back. That's a big loss to the shopkeeper. So what does he do? He has to monitor his stocks and then order if a particular item falls to the or below the reorder level. So reorder level means now, how do you know when to order? You have analyzed your sales. Just take, for example, just item A. Item A, you sell daily 10 items. Then if you have on you have a stock of say 50. So for 5 days you can go on. Average is 10. Some days 4, some days 7, some days 15, but the average is 10. So safely you can go for 4 days at least, right? In case there's a big sale, then you run out now. So for 4 days. But if the stock, the supplier takes 2 days to send the stock, or the delivery takes 2 days, then what happens? If you wait for that last day, and when the stock becomes zero, if you order, for the next 2 days, you have to turn back customers empty-handed. Therefore, you have to order beforehand. Keep those 2 days also accounted for, and then, so then there is a level. When the stock falls below 30, or 20 or 40. Whatever, depending on the sale, depending on the item and the sale, each item has a different reorder level. For a toothpaste, it will be like this. For a milk powder, like that. Fruits, differently. You can't get a lot of fruits and keep also. They are perishable. So you have to calculate. And then, anyway, coming back to this point, after that explanation, the reorder level is that. Now you understand what this reorder level is. So if one item reaches the reorder level before the end of month, then also he ordered. So it's not just one order per month. Maybe on the 20th, something falls below the reorder level, then 20th you order, then 25th another one, like that. Likewise, it goes. There are two conditions, two criteria. Then another one, third one. If a regular customer orders a large amount of goods, a delivery is ordered immediately. It's a regular customer. So it has to be a regular customer as well as a large amount of goods sold. Just because a newcomer comes and orders a large amount of goods, won't. He won't order. But if a regular customer orders, then he orders. So let's take that in order. Shopkeeper orders, put them into place, right? Shopkeeper orders delivery if the order will be on these conditions. If it is end of month. So that first point there, end of month. Or the second point is stock balance less or equal to reorder level. Or third point is regular customer buys a large amount of one item. So there's one condition there, one condition there. Here, how many conditions? Two conditions, two requirements, two criteria, or two conditions. They are called conditions. One is regular customer and also large amount. So if a regular customer buys a normal amount, then this is not true. This condition is false. So then he will not order. But a large amount by not a regular customer, no, a new one, then also he will not buy. Both have to be correct. Regular customer and large amount. So you will realize these things when you come to and or, how you compare. So we will put like this. Let A represent end of month. So for this, we'll put a symbol, a code, shortened form, A. Whole thing is A, end of month. Then B, reorder level reached for the second one. Then C, represent regular customer. So I told you two conditions, regular customer. C and D is large amount. Let's see how this C and D act. Then we can say X. X is right, the reorder level. Reorder, sorry, placing an order is X. If A, that means A is true. Let's look at this note to be easy to understand. A and B is true if both of them are true. A or B is true if one of them is true. A is true, not A is false. These are the things that you have to remember. And then true equals 1, false equals 0. So A, if you just say A, it is true. If it is false, you have to say not A. Right? So if you just say A, it's true. So in like that, it's A. If you just say A, that means end of month. So at the end of month, you will order. Or here is a gate or gate. That's how the logic circuit works. Later on, we will learn. I'm telling you in advance. What about that? Either A or B. What is B? Represent reorder level reached. Right? B. So either end of month or reorder level reached or these two together, C and D. I told you that regular customer buys a large amount of one item. That is, those two have to come together, and this and means both have to be true. Now here, if A is true, that is enough. We don't have to check whether these are okay. If A is true, that is enough, right? When or just one is, that is what this is said. A or B, the condition A or B is true if any one of them is true. So if either A is true or B is true or this is true, the whole thing true, that is enough. You don't have to check whether the others are true. Just one is enough. But if you say and, that is different. A and B is true if both of them are true. So here it is, C and D. These two both must be true. That is the meaning of and. So either this or this or this. It's nice. Huh? It's nice when you analyze and do it. Huh? Then there is task 4.01 from the textbook again. Convert the conditions in the following problem statement into a simple logic expression. Document can only be copied if it is not covered by copyright, or if there is, then that means copyright and permission has been obtained. There is copyright and permission has been obtained. So then only you can copy. When can you copy a document? A document can only be copied if it is not covered by copyright. So if the document is not covered by copyright, there is no owner of it. Right? Nobody claiming the rights. We can copy, no problem. Or else, there is copyright. There is copyright. There is somebody claiming the ownership, but you have taken you have obtained permission from him. Permission has been obtained. Then also you can copy. So the conditions are, now the shortened forms are: A is not covered by copyright. This one, I have underlined it here, not covered by copyright, A. B is covered by copyright. Covered by copyright, B. C is permission has been obtained, permission obtained. So that means X equals A. Because this or is there in the statement, if the or is there, that means either this or that. Copyright, that means B. A or, then within brackets, why? Because it's and here. B and C they have to be resolved first. B and C, the result of B and C or A. A or the result of this. That means result of B and C. Is it true or not? That's a way, right? Now there's an exercise for you. You also must do some work. No? There's no point in my talking all the time. Here X equals A, or I'm putting this A dash and C. Is it the same? Draw the circuits and compare the relevant truth tables yourself. Actually, because there is a small difference. This is why I want to show you. Students go wrong like this. When you say not covered by copyright, or there copyright and permission. This is not the opposite of this. Here there is copyright and permission obtained, but here there is no copyright and no need to obtain permission. So that is why this is wrong actually. This A dash or not A is not equal to B. B is a separate one covered by copyright. But you might, when you read the question, you might get the impression that not covered by copyright, or this is copyright. That means, okay, if this is A, this is not A. Opposite of A. No, that is wrong. So here you can do this and see. You will get the answer. So I will do this so that you know that. Then comes truth tables. What are truth tables? Truth tables are like the result of there are two, actually there are two inputs to a gate, except the NOT gate. Right? Except the NOT gate. See, I have explained it here. So when there are two inputs here, this is an example of an AND gate. The two inputs are A and B, and there are different values of this A and B. And you know that 0 and 1, how do we use 0 and 1? If it is true, if any condition is true, that is 1. If it is false, it's 0. And for AND, take this example. A and B, please come. I'm calling two people. A and B, they are seated nicely. Right on. A and B, please come. If anyone comes, for example, A comes, then A is 1. Doesn't come, is 0. So based on that, you have this truth table built up. So first, A doesn't come, B doesn't come, then false. The outcome, not satisfactory because none has come. Then the next one is A doesn't come, but B comes. One is come is 1. B comes. Are you happy? No, 0. Why? Because I said A and B, not one of you. A and B, both. So both have not come, just one has come. So not satisfactory, so it's 0. Then this time, then third time, A comes, but B doesn't come. Still not satisfactory, 0. And finally, the fourth time, both come. Then only I'm happy because that is what I want. I said A and B, please come. So now they have come, that's 1. That is how you build up the truth table. So, task 4.02. Without looking further on in the chapter, construct the truth table for the OR operator. So stop the video now. Do this task on your own. I'm sure you will do it. It's very easy, but just to make sure, 100% sure that you understood. If not, you can go through the rewind the video and look at it again. For the moment, pause and do it. Then we come to logic, circuits, and logic gates. When you are ready with the answer, you can check because I have given the or truth table later. The answer will come in a moment. So keep your answer ready to check with it. So logic circuits and logic gates here. NOT gate has one input and one output. Other gates have two inputs and one output. Like this is an AND gate, two inputs from this side, maybe A and B, and the outcome, maybe X or Y or whatever. Each input can have one of two possible values, 1 or 0. If the circuit is on, that is 1. If it is off, this is off, that is 0. Easy, very easy. It's a logic gate, the definition. A component of a logic circuit that has an operation matching that of a Boolean operator. So, NOT gate, as I told you, one input and the output is the opposite of A. That is why it said not. Good, not good. A, not A. And the truth table. So giving those results in a table, that's called the truth table. It is true, right? So for A, the outcome is, if A is 0, the outcome is 1. If the A is 1, the input is 1, the output is 0. Just the opposite of it, right? Then AND gate, You have A and B, and when you output, this is the way you write the Boolean expression A dot B. How do you get the dot? See, A and B dot, because this goes like multiplication. Say, this is A and B, these two, before the equal sign A. A into B, 0 into 0 is 0. 0 into 1 is 0. 1 into 0 is 0. 1 into 1 is 1. So it's like multiplication. And for multiplication in maths, you put a dot here. Am I right? So, and for that, A and B are the inputs. How do you get these 0, 0, 0, 1, 1, 0, 1, 1? It's like the binary counting. You can remember binary counting. 0, 1, 1, 0, 1, 1. Then if another row comes, 1, 0, 0, like that it goes on. So that these are the unique combinations. The values that A and B can have, the most number of values A and B can have, but unique. This never repeats. 0, 0 is not repeated. 0, 1 is not repeated. 1, 0 not repeated. 1, 1 not repeated. You can't have any other combination of A and B here. That's the only combination possible. Then what happens? We learned it earlier. A, we did earlier. So the outcome is only one. Only when both are 1, A and B are 1, the outcome is 1. Now let's learn something new. OR gate. Or A or B. So for A or B, you use the plus sign. A or B come. A or B come, I'm telling. So first, no one comes. As usual, both are lazy. No one is getting up and coming. So it's 0. The outcome is 0. But this time, second time, A doesn't come, but B comes. That's enough. No, I told A or B. A or B to come. So if 1 coming, it's enough. So it's 1. Then 1, the A comes, but B doesn't come. Still okay, happy. We put 1 here, outcome. And both come, it's no problem. No? Better, no? Can't say not satisfied. For 1, you have got 2, it's okay. So that's also 1. There are 3 1s here and 1 0, where for the AND, 3 zeros and 1 1. Okay? And see what happens. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. I'm not putting it here because 1 plus 1 is 2. But you are not worried about it, no? Because this is anyway okay, no? You don't have to worry. Both are there, so it's 1. Only these 3, you're not sure whether it's AND or whether it's plus or multiplication. So this is plus. We use the sign, the symbol plus A plus B. Here we have A dot B. Here we have A plus B, which means A or B. So A or B, the outcome, A or B. So when A and B both are 0, we call it like this, 0 or 0 is 0. In this case, we are saying 0 and 0 is 0. 0 and 1 is 0. But here we say 0 and 0 or, 0 or 1. Oh, this is wrong. But correctly. 0, okay. 0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. So 3 ones, as I told you earlier. Here 3 zeros, here 3 1. That is a A or B, given like this, A plus B. Then we get to NAND. NAND, as I told you earlier, like good, not good. Here this is AND, not AND. So the symbol, the shape, there is a small change here. You would have noticed that the NOT gate has this knot here, small knot around the neck, right? Like a tie. So that circle is here. Why is the same shape, or not? Easy. A dot B, the same outcome. I mean, you take in two stages. First, you resolve the AND part of it. Then you put a slash dash here. A dot B, bracket, within bracket, and then dash. That means this not here, the inversion. Not AND. Okay. So then what happens? That also is easy. You take the and take the opposite. Like if it is 0, 0, it's 1. And if it is 0, 0 and 1, it is 0 here. So that also becomes 1. Then here, 1 or 0, 1 and 0 is 0. Then this is the opposite. It's 1. And this one, what happens? 1 and 1 is 1 here. Then this must be 0. So this is the truth table for NAND. 1, 1, 1, and 0. For the AND, 0, 0, 0, and 1. Now let's go to the NOR gate, not OR gate. Same way. There's a NOT to make it OR. The symbol is the same. I'll help you how to remember. I'll tell you how to remember these symbols or the shapes. So not OR. So same way you put A plus B, like the OR gate. Then within brackets, you may put them in brackets and then put a dash. Make it not OR. So there what happens? Here the OR gate is 0, 1, 1, 1. So first one 0 or 0 is 1. Sorry, 0 or 0 is 0. So this must become 1. Then the next one is 0 or 1 is 1. Then this must become 0. This must become 0. Next is 1 or 0 is 1. Then the next one is also 0. 1 or 1 is 1. In that case, this is. So you will observe that the opposite of OR is NOR. 0, 1, 1, 1 becomes 1, 0, 0, 0. Like the AND, 0, 0, 0, 1 becomes 1, 1, 1, 0. All right. And now the special gate, XOR, exclusive OR gate. Shape is this, like the OR gate, but there's an extra. You can even remember like that X. In the XOR gate, there's an extra line parallel to this shape here. The same way, but the symbol here used is like this. Within a circle, the plus sign. XOR. Here it is slightly different. If the things are equal, then it's 1. If they are different, if they are unequal, then it's 1. If it is equal, it's 0. That means 0. This A and B, 0 means equal, then it's 0. If A and B 1, also 0. If A and B are different, not the same, not 0, not 1, it's 0 and 1, 1 and 0, different, then it's 1. So exclusive OR is that. But how are you going to remember that? Every student makes a mistake on this. Later on, you can't remember this truth table. The way to remember is like this. Imagine that you are calling A and B are seated there. You know the difference between, you know the meaning of exclusive. Exclusive coverage, exclusive report, exclusive interview. You may have seen on TV, news reports come like exclusively on such and such a channel. That means only that channel is telecasting or broadcasting that. If more than one, if another channel is telecasting, then you can't say it's exclusive. Or if somebody else, if the president has given an interview to only one person, that's an exclusive. We are given to two or more, not exclusive. So here, look at this. If A and B both don't come, then anyway it's zero. We always saw, then we are not satisfied. We are calling all of them to come, but not come. Then A doesn't come, but B comes. Okay, that's correct. Exclusive, only one person. And next time B comes, but A comes, but B doesn't come. All right, one person, exclusive. Last time, both come. That is wrong. That is not exclusive. There has to be only one person to call it exclusive. Now it's easy for you to remember the truth tables, the XOR truth table. Next step is you're going to remember these shapes. How can you memorize? Think of these two. It's enough. No? These two is a problem. Is this or and? Is this and or? So this is like the letter D. This shape is like the letter D. So letter D is in and. Right? And. So then when you know that this is the AND gate, then no need to worry about the other one. Automatically this becomes OR. Still, if you want some more confirmation, take this like a circle, complete this circle, semicircle here. Then it's like O, capital O, right? OR gate. All the others, of course, is, AND becomes NAND here. Then OR becomes OR here. Then XOR, the extra line here. Right. So that's a good exercise. You'll have to master this. See whether these truth tables are correct. Whether I have made any mistake. Because now also I corrected some. So see, if you can find an error, that's fine. Send an email. Or post it in the relevant forum. Now, what about this? Task 4.03. Draw a circuit where A and B are input to an AND gate, from which the output is carried to a NOT gate, from which there is an output X. Show that this has the same function as having one NAND gate. So these are two diagrams. One is the first one that is given. A and B are input to an AND gate. So A and B input to an AND gate. This is the AND gate. What is the outcome? A dot B. No, we already learned this. A dot B. Then from which the output is carried to a NOT gate. So this is the NOT gate. And what happens when it comes out? From which there is an output X. So X equals A dot B, this one, inverted. So you can put like this. It's called A dot B bar. A dot B bar. But you can also put like this. If this is difficult to put, you can put within brackets A dot B dash. Brackets needed because this dash is for both. Without the brackets, if you put, then that means the dash is only for B and not for A. So there's a big difference. A dot B dash. Big difference here, right? It's not the same as the one above, right? So now we have an outcome X. Now they are saying show that this has the same outcome as having one NAND gate. So here one NAND gate. So because A and B going through one NAND gate. What is the outcome? As I told you earlier, first you resolve the AND part. Take it into two. And then like this invert. So AND part is A dot B like this. A dot B and NAND becomes the opposite of that. So A dot B within brackets, the whole thing dash. So it's the same, no? The outcome is the same. So there can be like this. different models also, different circuits giving the same output. Example 4.02. Constructing a logic circuit from a problem statement or logic expression. Constructing a logic circuit from a problem statement or logic expression. So now we are going to do big things now. What is the problem statement? Here it is. A bank offers a special lending rate to customers subject to certain conditions. To qualify, a customer must satisfy certain criteria. Like these conditions, these are the conditions. The customer has been with the bank for 2 years. Right? The customer has been with the bank for 2 years. Two of the following conditions must also apply. Must also apply. That means this being true is not enough. Just because the customer has been with the bank for 2 years is not enough. So with that, that's why I put and here. And so two of the following conditions must also apply. One, the customer is married. The customer is aged 25 years or older. So if those two are there, it's okay. Otherwise, the customer is aged 25 years or older. The customer's parents are customers of the bank. So if those two also okay, enough. Right? Even if this is not, he's not married, if these two are correct, it's enough. Or else, customer is married, but customer's parents are customers of the bank also. That means the customer is aged 25 years or older is not necessary. If these two are either these two or these two or this and that. So three combinations here, no? Two of the following conditions must apply, also apply. So two of the conditions, two of three means there are three combinations. So let's take the symbols and shorten it. A means account held for 2 years. So for this very first one, we put A. If that is correct, if the bank account is more than 2 years, then A, account held for 2 years. Then B is the customer is married. So that's for this customer is married. And C is the customer is aged 25 years old or not, or older, this one. Then D is the customer's parents have an account. Customer's parents have an account. So all need not be. It doesn't say and all three of these. No, say two of the following. List two of them, enough. So X equals, now you know what X is. If the output X is if A and, that means A and, so because of this A and, then either B and C, either these two or B and D. B and D. The customer is married and D, or C and D, these two. Those are the three combinations possible. To take two of those. So then you have to put brackets like this: B and C, or B and D, or C and D. Right? This is the final the Boolean expression. So that how are we going to draw the circuit? So A. So we need A and the result of all these. That is why this big bracket here. All these have to become one in order to get A and this. Whatever the outcome of this A and. So A is on one side, A is going through the AND gate directly. There's an AND gate here. A is going through directly, but before that, for the others to go through the AND gate, they must go through these small gates also, B and C. So B and C or B and D. There's another gate here, B and D, or C and D. Then what happens? you can't have, we learned that there are only two inputs to a gate. So you can't have one OR gate having all three, this B and C and B and C or B and D or C and D altogether you can't have. So because of that, B and C or B and D one output, B and D or C and D another output. Those two output go through one OR gate. Then finally, that, so after resolving all this, there is one result that will go through this AND gate along with A. So A will come from there and the other, this part, this whole thing after evaluation will go from here to the AND gate, and that is the outcome. Right? So if I detail out some more, if I simplify it or extend it some more, it will be like this. A going through an AND gate, B and C, this one. This one also I am putting like this, B and C, outcome is there. Then B and D, here B and D or C and D. So I am putting B and D and or C and D through this, which gives an output here. With that, this B and C output will go to this OR. This and this. And then go to the AND gate. There's a small change here. I want to make it direct. Yeah, otherwise it's not necessary. And or, yeah, this or can be taken out. But there's only one input there. So like this. It's interesting when you reason out and do logic. Why can't I? I have made it. Yeah, I will. When I publish this, I will change this. This has to be just one. The outcome of this, or the outcome of this, or this. That will go through this AND gate. Outcome of this, or the outcome of this and this. That's how to accommodate three AND gates to two OR gates. See? All are there, not to worry. See? Two OR gates. So two OR gates, three AND gates, and finally the final gate is AND here. So you can double check like that. One AND gate here, that's the last one. This side, how many? 1, 2, and 3. 3 AND gates. So the 3 AND gates are here. And then also in between you have two OR gates for these 3. So there are 2 OR gates here. This is coming directly here. I have grouped it. So okay, I'll do the correction now itself. Ungroup there. That's done. And then how do we draw the circuit now? Based on this diagram, well, you don't have to do this. This is not even in the textbook. Understand and in between interim step. Otherwise, you can go through this straight away to this one. I told you 2 AND gates. Let's take it, try to get it on the same screen. User size. Yeah, now we can have it. A is coming from there. You can see that. B and C for this AND gate for B and C. Then this AND gate for this second one, B and D. B coming here like this, and then D coming from here. D from here, D is going like this. Remember that you have to put like this, not like cross a line. If it is not connected, it's not short circuiting, right? If it's not connected, you have to put a bend like this, going over that, fly over like bypass. So D is going like this to this AND gate, and B is also going to that AND gate. That is for this B and D. Then the other one, C and D, is from C it's coming to this, and the D also going to this. So that is one outcome of that. Then these two going through another OR gate. Then the outcome of that, or this, that's the second OR gate. Second OR gate, we have two OR gates, three AND gates, two OR gates, and finally the last one, another AND gate. So A and the outcome of this go through the AND gate. That's quite nice. Third example, 4.03. That is constructing a truth table from a logic expression or logic circuit. So you should learn now, you should be able to do this also, constructing a truth table. So truth table, we saw something like this, and this is the circuit. We have a circuit with three inputs for conversion to a truth table. So we can, this is the, to draw the how many rows. How do you know that how many rows now? Earlier in truth tables we had only 4 rows, no? For 2 inputs. Now there are 3 inputs here. 3 inputs. And then how many rows do we need? We need 8. How do we know that? Rows in the truth table, that is 2 to the power n. And n is the number of inputs. You can think of like this, number of inputs also. Easy to remember. 2 to the power inputs. Equals, and you can just say inputs. That easy to remember. Inputs, the inputs. The number is n. If it is 2, if it is 1, it's 2 rows. That is for the NOT gate, remember? NOT gate, only 1 input and a total of 2 rows needed. For AND, OR, NOR, NAND, XOR, those things, we have 2 inputs, so you needed 4 rows. But now we have 3, so it's 8 because 3 to the power 2. 2 to the power 3. 2 to the power inputs. Inputs are 3. So 2 to the power 3 is 8. There are 4 inputs, 2 to the power 4, which is 16. So if it is 3 rows, you have 8 rows, 2 to the power 3. And how do you fill these up? Like earlier, we had 0, 0, 0, 1, 1, 0, and 1, 1. But here, 3 rows like this. It's the same way, like by recounting, but easy method is take half of these 8 and put zeros. Half of it, that means 4. 4 zeros, then the other half, ones. Then you go to the next column, half of that also. Half of 4 is 2. So 2 zeros, 2 ones. 2 zeros, 2 ones. Then the next column, half of that is just 1. So 1 0, 1 0, 1 1, 1 0, a 1 here, a 0 there, a 1, a 0, a 1. That is how you get the individual or unique ones. So same way, I've done this for you here. And for the exam also, usually they give what I taught you, because in case they don't give, what happened? Then you say, no, you must give. All these years you gave, but it's not fair. You can't say that. You have to be, and then you will be the only student who will score marks for that question in the world, because everyone is expecting this, that the examiner will give. So you also must know better. Then what happens? How do we construct this? Look at the circuit. Take one by one. Take one by one. One gate by gate. First take is the AND gate. So A and B is a connection here. A and B. So A dot B, A and B. Remember? Right. So we have A dot B here. Then with an OR gate, it becomes A dot B dash. So we put that also here so that we can build up the values. Then you have B dash here because B is inverted by this NOT gate, B dash. Also here you get C. So B dash also we can calculate here. Then B dash C is this. And the final outcome is either this, not either, this and this is AND gate. So this is it. A dot B dash and the dot here, B dash dot C. So how? Now let's fill up these things. A dot B, how do you calculate A dot B? 0, the first row. First row is 0 dot 0 or 0 and 0 is 0. Then again 0 and 0 is 0. But now you will get confused. Now this is the, I'll get the colors. Then it's easy. Maybe I'll highlight this and this. These two, A dot B. So these 0 and 0, 0 and 0. Oh, I'm sorry. Sorry, what did I do? Take these two. A, 0. First row is 0 and 0. The answer is 0. Second one is also 0 and 0 is 0. Then the next third line is 0 or 1. Okay? 0 and 1. 0 and 1 is 0. Next, 0 and 1, 0. Next, 1 and 0 is 0. 1 and 0 is 0. Only these two are both ones. 1 and 1, 1 and 1. So the next two, last two are 1 and 1. Then you get A dot B dash, the whole thing inverted. So just the opposite of this. Isn't it? The opposite of this. So these, how many? 1, 2, 3, 4, 5, 6. And these two become zeros and the other 6 become 1. 6 ones and 2 zeros. The opposite of this. Next is B dash. B dash, how do you take? Opposite of this. So 2 ones. Again 2 ones. Again 2 zeros, 2 ones and 2 zeros. So that's how we put now. 2 zeros, 2 ones, 2 zeros and 1. The opposite of that. And the other one coming from B dash C. This one. B dash and C. So B dash is here and C is here. I'll highlight it. So that is easy. For the beginner, it's easy like this. B dash. Yeah, B dash, these two. Zero and 0 is 0. 1 and 1 is 1. I'll move the cursor one by one there. 1. Then the next line, 0 and 0 is 0. 1 and 0 is 0. 0 and 1 is 0. 1 and 1 is 1. 0 and 1 is 0. And 1 and 0 is 0. So there's only two ones. Yeah, both C and B dash are 1. Then the final one is this A dot B dash. dot B dash is this. With B dash dot C is this. So you highlight that. Easy. So I'll keep the cursor here and move. 1 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0. 1, 0, 0. 1, 0 is 0. 1 and 1 is 1. 0 and 0 is 0. 0 and 0 is 0. So this is the answer to this question. Okay. This truth table for this circuit. The in-between thing is this. You have to get this logic, Boolean algebra or the expression. Boolean expression you must get. Then only it's easy to do like this. This. A truth table to be converted to a logic circuit. Now we are coming to the another stage where we can draw a circuit from this truth table, the reverse of it. Earlier, what we did was we did up a truth table. We worked out the truth table from the circuit, but now from a truth table, we are going to draw a circuit. There are 3 inputs and an output here. So the 3 rows that produce a 1 output have the following values for the inputs. So shortcut 1. These 3 ones, you take only the ones. We take only the ones that are given as the output. 1 here, another one there, another one there. All the others zeros. The output is 0. Now the output whole thing is 0, 1, 0, 1, 1, 0, 0, 0. So these 3 are 1. Take the first one. That is 0, 0, 1. A dash B dash C. A is 0. Yeah, let's go through like that. A is 0. Yeah. B is 0. And C is 1. That is, then only get this 1 here. Zero, 0, 1. A 0, B 0, C is 1. Then the next one, this one. A 0, B 1, C 1. Okay. Third one here. A 1, here, A 1, B 0, and C 0. That's the third one. So we can construct our interim stage, right? Like the Boolean expression. A, not A. A is 0 means not A, no? If A equals 1, it's A. A 0 means not A. B 0 and not B. Right? And C equals 1 means C. C. All right. Not A and not B and C. Only we'll give this one here. Then second one is like this. Not A and B. Because B is 1 here. And C. C is also 1. So only A is 0. So not A. The others are normal. They are true. Here A is true. And B is false and C is false. Because B is 0. C is 0. So they are A and not B and not C. Then you write down the expression from there. The first one, A dash, because not A is A dash, dot B dash, because not B, B dash, and C, just C, without a dash. then or. It is or. Because any one of these will give 1. That is the idea. Any one of these. Either this or this or this. Where it is 1. The output is 1, x. Those are the ones. So, and this or that second one is not A. That is A is 0. B and C are 1. So, and B and C. We are going through this. A dash, B dash, dot C. Plus C is this for this or. Then not A, that is A dash, and B dot C for these two. Or then plus for that. A is there, the B is also there, and not C, only the C is B is, not B and not C. Not B and not C. So A dot B dash dot C dash. That is a final expression there. Then you can draw. No? Can you draw? Can you draw? That is for you to do. Draw the circuit for this. Then there's another task also. Okay, let's do this. I will do it for you. A little bit of spoon feeding. Right? This. Draw the circuit for this. We started from the truth table and arrived at this. Now we are going to draw the circuit. I have not done it. Table 4.04. Table 4.04. Yeah, we get this expression here. Based on this, how are we going to do the diagram? A dash, B dash, A dash dot. So how many gates? Let's see. I'll get you some drawings which I have kept in my library. I have these drawn. That easy. You don't have to draw again. You can just copy and take. So we need 2 OR gates here. One here, 2 OR gates. Then AND gates, how many? 1, 2, 3, 4, 5, 6. Is that all? No, we need NOT gates also. You see, NOT gates also for this. So let's take, and the inputs are 3, A, B, C. So A, C, B, C. First of all, we need, let's do, go through. Now, these must come later. These OR gates must come later. Within brackets, you must solve first. So we need 2 AND gates. So let's take as remember again, you can't put 3 inputs to an AND gate, right? So let's take first let's take one AND gate for A dash dot B. So A dash means we need a what? We need a NOT gate. We need a NOT gate. Make it A dash. Very small then. And put it here. Give you A dash. Mark it like this, A dash. And take B. Oh, yeah, take B dash. So we need another NOT gate. Here to get B dash out. Okay. One AND gate here. These two A dash dot B dash. Sector. You can adjust any way you like, but make it neat. Right? Then I'll connect these two. What will come out of this? That will be A dash B dash. Dash dot B dash. Okay. So this part is solved. Now that must go through with C to another AND gate. Because we can't put 3 into one AND gate. So 2 and 1 we have to get. C is not dash, no? C is not C, it's C. It's C, just C. So we can directly connect. But yeah, this has to come here. So what comes out of this? It's very interesting. Step by step, and it's easy. A dash, B dash. Correct. So this part is done now. Right? So likewise, then how do you do this? This or another one? We have to get an OR gate here. drawing. Freehand, I drew it, so but you all can do better than that. We can have the AND gate, OR gate here, connecting this. That's one input here. The other one, A dash. So A dash, we have to take from here. Take a connection from A dash. A dash, another line. P. Just B and C. So B we have to take from there, not here. You have to note that not from there. If you take from here, it will be B dash. You want B, you have to take from here. Before the NOT gate. And it has to be another. The outcome of that is A dash B. A dash B. That has to go again with C. So take another one from here. You have to put this curvy thing here. Right? Yeah, because these are not connected. I'm not good at drawing, so you better do it yourself. Let's take another line from C. Anywhere from here, it's C. My lines are crooked. That doesn't matter. You learn this. This is what I want. And another AND gate is needed. Because we have A dash B here, but another input has to go through this. C will come and take from here. Oh, how can we? Yeah, slight adjustment. Not a very good drawing, but when you are drawing on the exam paper, see, it's not like this. Just paper and pencil or pen. So easiest is to do this. All right. So then what? Now we have done these two. Another OR gate is necessary. And like this, we have to get that has to go through this and again, there are three inputs, no? has become one. This is another one. And this is another one. So there are three inputs now. I'm talking about the resolved one, the outcome of this. There are three inputs to two OR gate because you can't have in one OR gate. So this is one and another one should come for these three. So can you do that? I think you should be able to do. If you can follow the video, you can pause the video and or rewind the video and go back and see. If you can complete this, that's fine. Otherwise, we have to learn this again. We have the advantage of going back, repeating the lesson so many times until you master it. Then what is this task 4.04? This is a fairly advanced one. This is the coming to the exam style question. And our one has this is how you get the exam questions. And our one has a number of components that should all be working properly. For each component, there is a signaling mechanism that informs a management system that if all is well, no problem, like they say, all under control, like that. Or if there is a problem. So table 4.05, that is this table, summarizes the signal values that record the status for each component. In this kind of question, I advise you to read about 3 or 4 times. Even 5 times, be fine. Not only these algorithm questions and a few other topics, you better read the question about 5 times. Don't rush in. As you read, if you get an answer, don't write it. Just read it again and again. Then you will get that, you will realize that the answer is not what came to your mind. It's a little different. So when you read this again, you will get the idea. These are the inputs. A, B, and C are the input. One A is for the fan, B is for the internal light, and C is for the thermometer. If these are working, it's 1. Internal light working properly, 1. Thermometer reading in range, either working or in range, 1. And fan working properly, also 1. All the others, 0. That means fan not working is 0. A will be 0, not A. Like not A or A dash. Then B is 0 if internal light is not working. And C is 0 if thermometer reading too high. And the question, if the thermometer, this is the statement, if the thermometer reading is in range, right? Is in range, that means C is 1, no? Reading in range. C is 1. But either or both the fan and light are not working. The management system has to output a signal to activate a warning light on the control panel. That is X. X equals if these are true. If X is 1, if these are true. Draw a logic circuit for this fault condition. So what do we have to do first? First, we have to write down statements. If the thermometer reading, that is C equals 1, because this is a thermometer reading is, the thermometer reading is in range. That means 1. The thermometer reading C is 1, is in range, but for the but, that means and. Just because it's in range, it's not enough. And when it is in range, either fan A is 0. That means either, this is now, see, this is a good example that we have to read several times. At once, you will not get the idea here. But either or both the fan and light are not working. Either or both the fan and light are not working. So you can break it like this. Either fan A is not working or light B not working. That means either You have to break it down. Nah? Either the fan is not working or the light is not working. Or both. Either or both not working. That means light not working, both fan and light not working. Okay, so either one is not working or the other one is not working, or both not working. So you have to be very careful, very, very careful. This is a very tricky question. Then what? C equals 1. So now you make it as a statement. C equals 1 and this and is coming here. A equals 0 or B equals 0. After that, what? Or either that or both not working. Both is A equals 0 and B equals 0. See the difference? This is or here and this is and. So either or both. Either is not working means one of them. A is 0 or B is 0. So if B is working and A is not working even, that is true because it's OR gate. But here also, if both are not working, so this will cover each other like, it's very tricky. If one is working, then it will not be true, the whole thing. Both have to be on. Then the next step is draw these first. Okay. C. So C, take it as one input. C within brackets. And you take the and here and A dash. A is 0 is A dash or B dash. Then this or A dash and B dash. So either A dash or B dash or A dash and B dash. So draw these first. I'm giving a clue. First take those two and draw. So how? A dash is this because A is coming here and to put a NOT gate A dash and B dash same way. B is also B dash here. A and B or A and B. So again that is A dash is coming here. B dash is coming here. That's an OR gate. A dash or B dash. A dash or B dash. That is this one. Then for the other one, A dash and B dash. So A dash is coming from here and B dash is coming from there. So those two are there. Those two must go through this OR gate. That is this OR gate. Then these two are solved now. All these solved when it comes out here. Both are resolved. Then final AND gate here. That is this. With C, along with C. C dot C and this one input, whole thing coming here after resolving all these things and with C directly. That is the output. C dot A dash dot B, A or B dash or A and B dash. And the truth table. So I have done this, right? You go through it and see whether it is correct or if there is a mistake. If there is a mistake, then share it. Share them in the relevant discussion forum. I'll provide a forum there, discussion, or send mail to mcifernando@gmail.com if you find an error, right? So that's a challenge. So that is the end of this chapter 4. In the yeah. So then if you have any question, like of course you have the because the assignments. You have assignments, you have quizzes, homework, all that. So the tutorial is there. You can see the tutorial when if you click here, you will get it. And the notes are there. The video, and the exercises, Boolean algebra, many things. So I hope you will do this and complete successfully. So see you in the next video. Bye and good luck.